Each year, the world's factories churn out more than 430 million metric tons of plastic. Line that up as freight trains, and it would circle the entire planet 7 times over. Now here is a figure that should stop you cold. Fewer than 10% of all the plastic ever produced has been recycled. Everything else piles up in landfills, drifts through the oceans, and even settles inside our own bodies. Researchers have pulled tiny plastic fragments out of human blood, lungs, and arteries. In barely 100 years, a material that conquered the planet has started collecting inside of us. But in October 2025, a small group of researchers at a forestry school in northeast China put out a paper that left the engineering world staring in disbelief. They announced a brand new kind of plastic built entirely from bamboo. Not bamboo blended with oil, not a partial stand-in. A material that is 100% bamboo, tougher than ordinary plastic, ready to run on the factory machines that already exist, and able to rot away completely in plain soil in just 50 days. If you love videos about breakthroughs that flip whole industries on their head, please tap that like button. A great deal of work goes into making these. And subscribe so the next one does not slip by you. Why this matters runs far deeper than one new material. To see why engineers keep calling it impossible, you first have to understand how plastic took over the world, why every attempt to replace it has collapsed, and what makes this bamboo discovery so unlike anything that came before. The material holding the modern world together. Look at the phone in your hand, the tub holding last night's leftovers, the shell around your laptop, the dashboard in your car. Every one of them has something in common. All of them are built from plastic. And that is no coincidence. Plastic spread everywhere because it pulls off things no other material can. You can melt it and pour it into any shape you like. A bottle, a gear, a car bumper, a tiny clip buried inside a medical device. It costs almost nothing to produce. It will not rust the way metal does, rot the way wood does, or shatter the way glass does. It seals water out, holds electricity in, and shrugs off being dropped, heated, or left in the rain. Medicine leans on plastic in ways most people never stop to consider. Every syringe, every IV bag, every sterile wrapper keeping germs off surgical tools. Strip plastic away, and modern hospitals would barely function. Food is the same story. Plastic wrap keeps a loaf of bread fresh for weeks rather than days. It carries food across the globe without letting it spoil. It protects your drinks and keeps medicine clean. So when somebody suggests we simply ditch plastic, the honest question becomes this: what else can do all of that while still costing next to nothing to make? So far, the answer has been nothing at all. That is exactly why replacing plastic is such a nightmare. You are not merely trading one material for another. You are trying to yank out something that holds the whole modern world together. Ditching plastic would be like pulling every nail out of every building in a city. It all looks fine until you start, and then the whole thing collapses. But there is a catch, and it is a huge one. The very quality that makes plastic so handy is the same one that makes it dangerous. It refuses to break down. A plastic bottle you toss today will still be lying in a landfill hundreds of years from now. It will outlive you, your kids, and their kids as well. Rather than vanishing, it slowly crumbles into smaller and smaller fragments, too tiny to see, yet small enough to sneak into everything. Those fragments settle into rivers, into soil, and, as scientists keep discovering, into the bodies of living things. Fish gulp them down, birds eat them, and people breathe them in or swallow them through food and water. The material we built our world around is now turning up inside us, and nobody yet fully understands what that does to our health. So the world is trapped. We built everything on top of a material that never leaves, and every year we make even more of it. The push for something better is not just about being kind to the planet. It is about the fact that plastic is now sitting inside our bodies, and that is a problem that will not solve itself. But cracking that problem has proven far tougher than anyone imagined. Every single attempt at a replacement has slammed into the same wall, and that wall is where this story turns next. Every green substitute ran into the same wall. The bioplastics industry has been chasing this problem for decades, and nearly every time it has come up short in the same way. The materials they cook up are either strong but refuse to break down, or they break down but are too weak, or they manage both while costing far too much to make in bulk. The best-known bioplastic goes by PLA, short for polylactic acid. It is made from fermented cornstarch. It can break down, but only inside a special facility that holds it above 58 degrees Celsius for weeks on end. Toss a PLA cup into your garden or an ordinary trash heap, and it will just sit there for years. It looks and behaves exactly like regular plastic. PLA carries other baggage too. It cracks easily when dropped. It cannot cope with high heat, and it comes from corn, which means you are burning farmland to grow plastic instead of food. Raising corn for plastic while people around the world struggle to find enough to eat is not a plan that works for the whole planet. Another candidate is called PHA, which stands for polyhydroxyalkanoate. It breaks down more readily than PLA, which is a plus, but it runs several times the price of regular plastic, because making it means a complicated process that uses bacteria to grow it. When something costs 5 times as much as the thing it hopes to replace, companies simply walk away. PHA has been stuck turning out tiny batches for niche uses for years. Starch-based plastics come with their own flaw. They dissolve in water, so you cannot use them for anything that might get wet. Picture how useless a water bottle would be if it melted in the rain. Cellulose acetate holds up better, but making it takes harsh chemicals, which rather defeats the point of building something green. Every approach has run headfirst into the same wall. You can build something strong. You can build something that breaks down. You can build something cheap. But nobody could make something that pulled off all three at once. The real trouble was never a shortage of good ideas. The trouble was chemistry at its deepest level. Nobody had cracked how to take a plant material and rebuild its very building blocks into something that behaves like plastic, without piling in chemicals that wreck the whole point of going green in the first place. Think of it as trying to turn a stack of wood into a steel beam. You can see the wood sitting right there. You know steel exists, but you cannot just bend the wood into a new form and call it steel. You would have to completely rebuild what the wood is at the tiniest possible level, and nobody knew how to do that with plant material and plastic. That is the wall the team in Harbin, China, just smashed through, and the way they pulled it off is what stopped engineers around the world in their tracks. The breakthrough nobody saw coming. The research sprang from a place nobody would have guessed. It was not some giant oil company. It was not a Silicon Valley startup. It was not some hidden government lab. It came out of Northeast Forestry University in Harbin, China, a school that mostly studies trees and forest science. Haiping and Dawei Zhao led the work. They teamed up with a group at Shenyang University of Chemical Technology. Together they set out to try something with bamboo that most material scientists had abandoned years earlier. Here is why bamboo was so stubborn to work with. The core building block of bamboo is a substance called cellulose. Cellulose is what gives plants their shape and their strength. It sits inside every tree, every leaf, every blade of grass. In bamboo, the cellulose molecules are chained together by tiny links, called hydrogen bonds. Those bonds are astonishingly strong. They are what let a bamboo stalk stand tall and bear heavy loads in howling wind. But those same bonds are exactly what make bamboo so hard to reshape into anything else. The cellulose is locked in place. You cannot simply melt it and pour it into a mold the way you can with ordinary plastic. Try to force bamboo into a new shape, and it snaps rather than bends. Other scientists had attempted bamboo plastic before, but they always leaned on a shortcut. They blended ground-up bamboo fibers with ordinary plastic glue. The bamboo lent some strength, but the plastic glue was what actually held everything together. What came out was half bamboo, half oil. It was a blend, not a true replacement. And because that plastic glue was still inside it, it never really broke down in nature. Wu and Zhao took a completely different path. They did not blend bamboo with plastic. They transformed bamboo into plastic. And they pulled it off in 2 steps, both simple and clever. Step 1. They soaked the bamboo cellulose in a special liquid mixed from zinc chloride and formic acid. This liquid does something remarkable. It pries apart the hydrogen bonds, pinning the cellulose molecules in place, yet leaves the molecules themselves unharmed. Picture patiently untangling a mess of knots in a fishing net. The net itself stays intact. The strands are still strong. They are simply no longer locked into that rigid shape. Step 2. They stirred in ethanol. The ethanol works like a guide. It nudges the freed cellulose molecules toward each other so they link up in an entirely new arrangement. As they reconnect, they forge fresh bonds, even stronger and tighter than the ones in the original bamboo. The molecules essentially rebuild themselves into something better. What comes out looks, feels, and behaves just like regular plastic, but it is made 100% from the molecules that were already sitting inside the bamboo. No plastic glue mixed in, no oil-based chemicals added, no toxic waste left behind. They named the new material BM plastic, short for bamboo molecular plastic. The name tells you both where it comes from and how it is made. But a catchy name and a good story count for nothing without hard numbers to back them up. And the numbers are exactly what stunned the engineering world. The test results that silence the skeptics. Plenty of materials dazzle in a lab. Most of them fall apart the moment you try to use them in the real world. BM plastic did not follow that script. Its test scores came in so strong that engineers who had spent entire careers around ordinary plastic had no choice but to take it seriously. A material out of a forestry school outmuscling petroleum plastic in strength tests is not something anyone had penciled in. The strength figures were impossible to brush aside. BM plastic can withstand a pulling force of 110 megapascals. That is roughly twice as strong as PLA, the corn-based bioplastic. It also beats high-impact polystyrene, a plastic found in countless everyday products. For a sense of scale, 110 megapascals edges close to the strength of certain grades of steel and aluminum used in cars and airplanes. This is not some fragile plant plastic that cracks if you look at it wrong. It is a genuine structural material that can carry real weight. It shrugs off bending too. It hit 6.41 gigapascals when they bent it. That is a technical way of saying it does not warp or sag when weight presses on it. In fact, it outperformed ABS plastic on this test. ABS is the tough stuff used in car dashboards and Lego bricks. If you have ever stepped on a Lego barefoot, you already know how strong ABS is. BM plastic is even better at keeping its shape under pressure. Heat was the next hurdle. BM plastic holds its shape at temperatures above 180 degrees Celsius. The researchers parked samples in 100 degrees Celsius heat for 7 days straight with no cracking whatsoever. They also plunged samples into strong acid, and the surface came through undamaged. Try any of that with a PLA cup, and it would warp, crack, and disintegrate within days. BM plastic just sat there, perfectly fine. The material also soaks up a lot of energy before it fails. Scientists refer to this as work of fracture, and BM plastic reached 80 kilojoules per cubic meter. That tops both regular plastic and most bioplastics on the market. In plain words, it can take a real hit without shattering. That counts for a lot in things like car parts, phone cases, tool handles, and anything likely to get dropped or knocked around. Then came the number that grabbed the most attention from anyone who cares about the environment. BM plastic broke down completely in ordinary soil in about 50 days. Not inside a special facility, not inside an industrial composter, just in plain dirt, like a leaf drifting off a tree and quietly returning to the earth. After roughly 50 days, the material was essentially gone. And there is something even more surprising here. When they recycled it using that same liquid process, the recycled material held on to about 90% of its original strength. Ordinary plastic grows weaker every time it is recycled. That is why recycled plastic tends to end up in low-value goods like park benches. BM plastic dodges that problem. You can recycle it again and again, and it stays nearly as strong as the day it was born. The research team laid out all of their data in a public paper in Nature Communications. They showed every test result, every number, every step of the process. They did not ask anyone to just take their word for it. They let the entire world verify the work firsthand. But none of those numbers would matter if the raw material could not support making it on an enormous scale. And that is where bamboo holds an edge almost no other plant can match. Why no other plant comes close? The pick of bamboo was anything but random. You cannot just drop in some other plant and expect the same outcome. Bamboo carries a rare blend of traits that make it ideal for this job. And just as crucially, it comes with a supply chain that is already built and ready to run. No other plant on Earth grows faster than bamboo. Some varieties can add more than 1 meter in a single day. And no, that is not a typo. You could genuinely watch it grow if you sat still long enough. And once you cut it down, it springs right back from the same roots. There is no need to plant fresh seeds, clear new land, or lay down irrigation. A bamboo forest fully regrows in 3 to 5 years after cutting. Set that against a pine tree, which needs 25 to 30 years to reach cutting size. And while a corn crop must be replanted from scratch every year, bamboo just keeps returning on its own, again and again. Bamboo also yields about 5 times more plant material per hectare than a standard timber forest. It pulls carbon out of the air as fast as, or faster than, many kinds of trees. And it thrives on land that is useless for regular farming. That means it does not steal space from food crops. This is a big deal, because corn-based bioplastics like PLA get slammed for eating up farmland that could be feeding people instead of feeding a factory. China holds the largest bamboo resources on the planet. More than 7.5 million hectares of bamboo forest stretch across roughly 20 provinces. The country is home to over 500 different bamboo species. China's bamboo industry already brings in close to 320 billion yuan a year and supports more than 7.5 million farmers who rely on it for a living. That means the systems for growing, cutting, hauling, and processing bamboo already run at massive scale. No one has to build them from scratch. This matters more than you might expect. Plenty of brilliant new materials die, not because they fail in the lab, but because nobody can make enough of them cheaply. If your amazing new material depends on a rare plant that only grows in one tiny corner of the world, you will never make enough to replace hundreds of millions of tons of plastic. But bamboo grows all over the globe. It stretches across enormous parts of Asia, Africa, and South America. The world holds around 22 million hectares of bamboo forest in total, spread across many different countries. Bamboo is already harvested at huge scale for things like building materials, furniture, flooring, paper, and fabric. The chain for growing it, cutting it, moving it, and processing it is already up and running across much of the world. That means companies would not have to build an entire new system from the ground up just to start using bamboo plastic. So bamboo is one of the very few materials that is both excellent for making strong plastic and available in staggering amounts right now. It brings the performance, the supply, and the farming system all in a single bundle. But having the right plant and the right chemistry still is not enough. The real question is whether you can actually make this material in normal factories using machines that already exist. From the lab bench to the factory line. Racking up great numbers in a lab is one thing. Being able to make something in a real factory with real machines is a whole different challenge. This is exactly where most bioplastics collapse. They demand special equipment that ordinary factories simply do not have. BM Plastic does not carry that burden. It can run through injection molding machines, which is how most plastic products on Earth are made. It can be cut, drilled, and shaped using ordinary tools. It can be pressed into flat sheets or intricate 3D forms. The researchers proved it by turning out lampshades, gears, packing containers, and decorations, all on machines that already existed. They did not swap out or upgrade a thing. This is enormous. Most new bioplastics need brand new production lines, custom molds, or conditions that normal plastic factories cannot deliver. That means a company would have to sink millions into new machines before making even one product. BM Plastics skips that whole step. If you already own an injection molding machine, you could start making bamboo plastic products tomorrow. The whole process also runs at room temperature. That might not sound like much, but it is. Heating plastic ranks among the biggest costs of making it. Regular plastic factories rely on giant ovens and massive heaters to melt their material. BM Plastic needs none of that. No blazing kilns, no pressurized tanks, no towering ovens. That alone saves a fortune on energy. The chemicals in the process, zinc chloride and formic acid, are common and cheap. The ethanol can be captured and reused. Nothing about the process calls for rare or costly materials. The researchers put the cost of making BM plastic at roughly $2,300 per ton. Regular plastic runs about $1,200 per ton. That is nearly double, which sounds like a deal breaker. But two things shrink that gap. First, the cost will fall as production scales up and grows more efficient, the way it does for every new product. Second, that $1,200 price for regular plastic ignores the damage it causes. Fold in the cost of cleaning up pollution, the health toll of microplastics, and new government fines, and the true cost of regular plastic could reach $2,400 per ton by 2040, according to one study. The reaction to this material has been quick. China has been getting ready for this moment for years. In 2022, the government rolled out a plan to swap plastic for bamboo. In 2023, it released a 3-year action plan. Real products are already rolling out. Bamboo fiber tableware exports climbed 35% in 2025. Bamboo pipes are going into cities to replace steel and cement. A bamboo drone even took flight, with bamboo making up 25% of its body. It came in 20% lighter than carbon fiber and cost roughly 1/4 as much. Meanwhile, global talks over a plastics treaty fell apart in 2024. Countries could not agree on how to rein in plastic production. The message was unmistakable. Do not sit around waiting for rules to fix this. Whoever builds the replacement first, country or company, will own the market. There are still real hurdles. BM plastic is rigid, which is perfect for solid parts but not for flexible things like plastic wrap or thin bags. It has to last for years in use before breaking down after disposal, and that piece still needs work. Scaling from a lab up to millions of tons is a gigantic job that eats time and money. But no bioplastic has ever brought together this much strength, this kind of breakdown, this level of recycling, this ease of manufacturing, and this scale of supply all at once. Not one. The world spent 100 years building its dependence on plastic. It will not disappear overnight, but for the first time, there is a material that hands you better performance and sustainability in the very same package. It does not force companies to give up something good, it offers them something better. And that is what real change actually looks like. If this video shifted how you think about something you touch dozens of times a day without ever wondering where it came from, drop a like and subscribe for more. Switch on notifications so the next one never gets past you. There are related videos waiting on the screen right now if you want to keep going. Here is a question to chew on. If a grass that grows 1 meter a day was sitting there the whole time as the answer to the plastic problem, what other solutions do you think are hiding out in nature, just waiting for someone to ask the right question? Tell me in the comments.